my presentation, I decided to talk about the Fibonacci sequence. First of all, my name is Danae. It's nice to meet you all through the internet, and let's get started. All right, so first of all, what is the Fibonacci sequence? So it's essentially the sequence listed here, 0, 1, 1, 2, 3, 5, 8, 13, 21, etc., etc. The sequence is created essentially by taking each term and adding it to the previous term to create a new term. So you have 0 plus 1 equals 1, 1 plus 1 equals 2, 1 plus 2 equals 3. You guys know how to do addition. And it essentially goes on to infinity because it is a recursive sequence. So essentially what that means is that you take each bigger and bigger term, add them together to create an even bigger term. So essentially what you're doing is adding infinity to infinity infinitely. So you can see how that would increase infinitely to infinity. Okay, so now anytime you talk about the Fibonacci sequence, you got to talk about the golden ratio and the golden spiral. So essentially the golden ratio is created by taking each term of the Fibonacci sequence and dividing it by that previous term. These ratios approach 1.618, which is the golden ratio. You have these examples down here. It's like 2 divided by 1 equals 1. Obviously, we're not going to start with 1 divided by 0 equals nothing. You can't divide by 0. So we start with 2. 3 divided by 2 equals 1.5. 5 divided by 3 equals 1.67, 8 divided by 5 equals 1.6, and again that goes on to infinity and very slowly approaches that golden ratio. Now one thing I will say is that the golden ratio isn't exactly 1.618. It obviously has a lot more numbers in there. What it is exactly is 1 plus the square root of 5 over 2. All of that over 2. So obviously it has a lot more terms in there, but basically the only numbers you really need to know are 1.618. Another thing I'll mention on this page is that you can see that 5 divided by 3 is much greater than 1.618, whereas this is 3 divided by 2 is lower, and 8 divided by 5 is also lower. So you know, these terms don't have to directly approach 1.618. They can kind of dance around it a little bit. But once you get to a certain point, they will naturally approach that longer golden ratio. Okay, and next, the most interesting thing about the Fibonacci sequence, the golden spiral. Okay, so essentially there's 2 ways of finding the golden spiral. First, you can do what's shown here, which is pretty common. You take each term of the Fibonacci sequence and create each of these squares by taking it a number in the sequence times itself. So, for example, we have 21 by 21, 13 by 13, 8 by 8, 5 by 5, 3 by 3, 2 by 2, and then 2 squares of 1 by 1. So, essentially what this is it's just creating this spiral by going through each of these squares, and actually it starts at 1 by 1 and goes outward. So what this is known as is it's a logarithmic spiral, and the growth rate of this spiral itself is actually the golden ratio. So basically what this means, and this is the other way of finding the golden spiral, is just by starting at the starting point of your golden spiral. It can be anywhere, and every quarter turn you take, you increase by 1.618. And you can see how this is kind of naturally happening within these squares that we've created. But again, these squares that we have here are kind of an easier, less complex way of finding the golden spiral, so this is usually what you see people do. One thing I will say as well is that when you start at 1, obviously you're going outward instead of inward. So this actually goes on to infinity, just like the Fibonacci sequence. So the next one would be 33 by 33, it's like 54 by 54. It gets, infinitely larger, just like the Fibonacci sequence. All right, and now we're going to talk about some real life examples. So obviously I've got a little quote here. This is from, I want to say Wikipedia, but that's fine. Essentially, if you count the number of spirals that are on a pine cone to the right, and then count the number of spirals going to the left, you end up with two adjacent numbers in the Fibonacci sequence. So usually that's either 5 and 8 or 8 and 13, but it can also be smaller, like 5 and 3, or it can be much larger if you have a bigger pine cone, like 21 and 13, or even 33 and 21, although obviously that's not really common. Pine cones are actually very interesting because they grow in a very specific way every time, so that will happen pretty much every time unless there is some sort of genetic issue with the pine cone or the tree. And then also you have a lot of flowers that more specifically follow the Fibonacci sequence by themselves. So buttercups, lilies, irises, delphiniums, corn marigolds, asters, and daisies have petal numbers which coincide with the Fibonacci sequence. I want to say buttercups are like 5, lilies are lilies are 3. You can look all of these up. It's very interesting, but we don't have like all the time in the world to talk about every flower. So next I'm going to show some good examples of the golden spiral. So like I said, there are some flowers that have that golden spiral. You can see that sunflowers are one of them. But if you also, they are very similar to pine cones. If you count the ones that are going outwards, like here, you get like, usually it's like 54. And if you count the ones that are going inwards, you get like the next number, which would be 33. Another example is a nautilus shell. So nautilus shells are very interesting. I cannot remember if they are specifically golden spirals. They can be. They are not always, I don't believe, but they are a very good way to kind of see how nature is affected by both the golden spiral and the Fibonacci sequence. And next we're going to talk about some bad examples. So obviously we've got a little joke on the right here, Family Guy death pose, but on the left you also have the Mona Lisa, which is one of those things that you see people talk about a lot with the golden spiral. But honestly, unless you're looking at some of those examples we talked about just a second ago that are very prevalent in nature, you're not going to see a golden spiral. What you're going to see is a logarithmic spiral. So the Mona Lisa may have a logarithmic spiral in her face that just so happens to look like the golden spiral if you turn it a specific way. But that does not mean that she was specifically made by Van Gogh, I want to say, to be the golden spiral. And obviously the Family Guy death pose was not made to be the golden spiral, but there is a lot of discourse online about people making up golden spirals, and this is kind of like a joke about that on the right here. I just thought it was funny. I had to include it. All right, so next we're going to talk about some of the background of the Fibonacci sequence. So it actually has a lot of history. So first of all, obviously it's named after Fibonacci, who quote-unquote discovered it. We'll talk about that in a second. And it was named after actually a man named Leonardo da Pisa, who essentially just decided he wanted his name to be Fibonacci one day. And he discovered that sequence. It was introduced, well, he quote-unquote discovered that sequence. It was introduced in his book Liber Abaci in 1202, which essentially means Book of Calculation. However, the golden spiral itself was discovered as early as 300 BCE by Euclid in his book Euclid's Elements. You can see right here, this is like the famous picture from Euclid's Elements. I'm not including the rest of the picture because it is not PG-13 and I don't really want it in my presentation. However, what's really interesting and why I'm saying quote-unquote discovered is that the Fibonacci sequence was already known to the Indians since the 6th century. So this is kind of a common thing with especially Englishmen, quote-unquote, discovering things that India and other parts of Asia had discovered literal centuries ago. So this just kind of continues that storied history. All right, and next we're going to talk about our real-life example of the Fibonacci sequence. So it's actually heavily used in cryptography, which I thought was really interesting. Cryptography is just the practice and study of techniques for secure communication. So basically, it's just a way of encoding. It's used to generate random numbers. That's because it increases to infinity and quite literally has infinitely many random numbers. Obviously, it skips a few numbers, but it has a lot of random numbers in it. It creates sequences for hashing. A hash function is a function that can be used to map data of any arbitrary size to a fixed size value. So an arbitrary size would be the Fibonacci sequence, and then you would map it onto a fixed size value. It illustrates concepts that are related to, like, basically algorithmic complexity and efficiency. All that means is that it's really good for beginning coding lessons. Okay, and we're coming to the end. Now we just have some fun facts, or at least I think they're very fun. The largest known Fibonacci prime, which is a prime number in the Fibonacci sequence, was the 201,107th term, 201,107th term, which had 42,029 digits. That was actually found September of last year. However, the largest known probable Fibonacci prime that hasn't been found yet is the 1,036,000, no, I read that wrong, 10,367,321st term, although we don't know exactly what its size would be since it hasn't been found yet. And then finally, there's an infinite number of Fibonacci sequences, which are known as the in-step Fibonacci sequences. The two-step Fibonacci sequence, for example, is known as the Fibonacci sequence, and that try at the beginning is because it takes 3 terms and adds them together to create a new term, just like how the Fibonacci takes 2 to create a new term. So yeah, thank you for listening to my video.